A show of hands, how many think that there is an alligator that makes this sound? Not so many. Now, take a second to think about this picture. How does it make you feel? Bothersome, right? It's unrealistic. It's very difficult for us to accept such image. When I studied quantum mechanics, I came about this picture. It made me uncomfortable just the same way as the previous picture made you uncomfortable. What does this picture mean? It says, and according to physics, that it is accepted that light can be both particle and a wave at the same time. How is that possible? You know, an ocean wave is a wave, and a rock is a rock. How can a wave be a rock, and a rock be a wave at the same time? Not only that, what quantum mechanics says, that a wave sometimes can behave like a rock, and sometimes can behave like a wave, and sometimes it could be a third option. Imagine you're at the beach and an approaching wave all of a sudden turns into a rock. That's crazy. Or if somebody throws a rock at you and then just before hitting you, it splashes into water. There's no way this could happen. We don't experience that as humans unless you see it in the Matrix movies or something. So why scientists have accepted such crazy idea or concept in such field of science? Well, maybe to find an answer to this is to look into history. For a long time, people thought that light is made of particles. And then all of a sudden, Descartes showed that light can be modeled as a wave propagating through a medium, which he thought it was a universal medium, and he called it plenum. I'll come back to this plenum stuff later on. But then Newton came along, and you probably heard, he spent a lot of time studying light. He spent over 30 years just studying light and the nature of light. And then he concluded that light must be particles. That is, light beams are made out of particles. At the same time, Huygens was also investigating light. But he showed that light is made out of waves. So it behaves like a wave. It's not a particle. But back then, Newton has a much stronger position. Newton was a very respected, well-established scientist. He have made so many accomplishments. So the wave view of light was ignored because Newton said light is a particle, so we cannot dispute that. And imagine it took 200 years after Newton died to make people comfortable to say that he was incorrect. 200 years was wasted just because people trusted what Newton said without questioning that. But luckily, over time, a lot of evidence surfaced that light behaves like a wave, and that was in the mid-19th century. And then comes Einstein. I call him the troublemaker. Einstein said, sorry guys, light is made out of particles, and not only that, I'm calling them photons. But then he was faced with a dilemma. How can he justify that all the evidences over the past 100 years that showed, or all the experiments that showed that light behaves like a wave, all of a sudden now he's saying that it's a particle, and he has experimental evidences shows that light is a particle. He said, guys, let's compromise, and I have a clever idea. He was very creative, and he said, well, let's call it both. Let's just say light behaves like a wave and a particle at the same time. And this is where the concept of particle-wave duality was born. It was born from Einstein and his creative thinking of what light could be. Now, duality is not new. It is deeply rooted in human cultures. We have many examples that shows duality throughout history. If we take centaurs as an example, it is believed that the idea of centaurs was a reaction to people who never saw a human riding a horse. So horse riders from far away, and because they didn't understand what that meant, they thought it was a creature that is half human, half animal. But then, of course, when the rider came closer, they realized it's just two creatures on top of each other. What quantum mechanics is telling us right now is to accept that light is like a centaur. It's both wave and a particle at the same time. Now, light, or theories about light, were not the only ones that faced such drama. There are other theories that have similar or face similar pattern. If we take, for example, ether, since the beginning of human thinking, ether was proposed as a medium that fills empty space throughout our universe. They thought it can't be vacuum. There has to be something that fills all the empty space in our universe. And they gave it a name and they called it ether. Now, in the 19th century, the view of light as a wave became strong. But for that to be supported, there was a need for a medium for the light waves to propagate in. And this has to be a strange medium. It has to be invisible, and it has to be infinite. And it has to be something that does not interact with physical objects. So now we're faced with another dilemma: is how can you even imagine such material in existence? So there was a long debate throughout history whether ether exists or not. Some people said yes, it does exist. Some people say no way, that's not possible, it's not realistic. But then comes Michelson. Michelson took it upon himself once for all to settle this debate. So he came up with a very clever experiment to measure or detect ether. And he tried tirelessly to measure ether, but he couldn't. So at the end he said, well, I gave up, and I'm saying that there's no ether. It does not exist. But then at the same time, Lawrence said, well, just because we couldn't measure it, it does not mean it doesn't exist. Maybe there's something wrong with the experiment. And he came up with some explanation to justify why ether could not be detected through this specific experiment. But most people did not believe that, so what most of the scientists decided to is to look for alternatives to how can light travel without such medium. And then comes the troublemaker again, Einstein, and he finds a very convincing way, using his relativity, to explain why Michelson could not measure ether. He also said it's not needed. Now, what does that mean? He meant, or what he said, guys, look, we've been crazy enough to accept the concept of light duality, so why not just accept that light just travels in vacuum at constant speed? And this is where the speed of light came about. So he just proposed that another solution, another crazy solution to the problem. Now, what does that tell us? It tells us that science is always in progress. We should not take scientific theories for granted. You have witnessed how scientists went back and forth between different theories throughout history. What if new ideas come up? What can we do? Even Einstein himself, when he said that we don't need ether, and this is during his when he was working out his special relativity theory. Later on, when he developed his general relativity theory, he realized, well, we need something similar to ether. So even Einstein changed his mind later on about some medium that should be in empty space. So could ether be the space-time continuum that Einstein talked about? Could ether be dark energy that now a lot of people talk about? We don't know. And I hope maybe someday somebody in a TED Talk would tell us what ether is all about. Now, scientific theories are, the best possible or best available explanation to things as we know them now. We should not take them for granted. Scientific theories does not provide absolute truth. It's just telling us what we know so far. So, and I hope that message gets across to a lot of people, because a lot of people just think just because an accepted theory is there, we think that's the absolute truth. Well, that's not the case. Now, I should also clarify that the term or the expression scientifically proven is a contradiction in terms. There's nothing scientifically proven. What we know is basically what the experiments are telling us. But that does not mean that that's the absolute truth. Now, in traditional schools, students are focusing on learning or understanding accepted theories. It is very rare that students are being taught how to challenge these theories and models. We should not teach students what to think. We should teach them how to think. And when examining any theory, whether it's physical or biological or chemical theory, you should always consider or question the assumptions. What were the assumptions when they were discussing this theory? Also, you should always question the way the test was done. Not only that, also the way data was collected. Remember Michelson experiment? Initially, he thought that his experiment proved his theory, but then it turned out it was wrong. And this experiment have been repeated so many times. He tried in the mountains, he tried in a cave, he tried in the desert, he tried everywhere, in different dimensions, different spaces. Even others, not only himself, others have tried it, just to make sure that the test is correct. And this experiment is famous or known to be the most famous failed experiment in history. So even though he failed, he still was recognized. Also, we should look into, or we should always question interpretations. Just like anything else, observations and data are open to different interpretations. Just to give you an example, quantum mechanics, in quantum mechanics there are 10 interpretations for quantum mechanics. What does that mean? Well, to be frank with you, it means we don't understand quantum mechanics. Otherwise, we wouldn't have 10 interpretations for quantum mechanics. So don't feel bad if you don't understand quantum mechanics. Some of the smartest people have said they don't understand quantum mechanics. I can give you an example. Feynman, he's a Nobel Prize winner in physics, and he said he does not understand quantum mechanics. Duality does exist. It's not just in our imagination. An object, such as this cylinder in this picture, can produce two forms of shadow at the same time. We can have a circle and a square in one setting. What does that mean? It means it does exist, but there are also other alternatives. The picture of particle wave duality does not make me comfortable. And I would like to share with you an alternative view or alternative theory, to which instead of having a centaur, you know, a figure, we can have a particle surfing on a wave. And this theory is known as the pilot wave theory, which was proposed initially by Duality in 1927 and then rediscovered again by Bohm in 1952. What this theory tells us that there is both a real particle and a real wave, but the wave actually influences how the particle behaves. This concept has been recently demonstrated experimentally by a group at MIT, and this is a video to show you how this happens. But basically, a group at MIT managed to produce a droplet that bounces on a surface of liquid. And as this droplet bounces on that surface, it creates waves. And then they were able to demonstrate that these waves actually guide the particle as it moves or as it hovers over that wave. So after all, you know, it is possible to have an alligator that makes bird sound, only if we think that the bird is actually just on top of the alligator. It's not actually half alligator, half bird. I hope I have sparked the Einstein in you to think about the nature of light, because we don't know or we don't fully understand what light is. And maybe one of you someday will come up with an alternative theory to explain the behavior of light. Thank you very much.